Lesson 2 is extrema on an interval. So if you recall, Unit 5 is still all about derivatives. In 5.1, we talked about mean value theorem. And now we are looking at extrema on an interval. And so remind me, derivatives. Do we know that derivatives find mins and maxes? Is that something we know at this point? And I know that's a silly question for me to ask, but I'm so confused in my calculus curriculums this year versus last year.
Yeah.
Maybe, maybe not.
Because if you
It
make
sounds
it
we
We
equal
did
familiar.
the absolute value. I mean, the derivative of velocity would be. We were kind of doing that where.
Which same idea,
Yeah.
okay.
it's like
But we
that.
haven't maybe, I don't think we've explicitly talked
I
about
think
it
you
then.
definitely said it. I don't know if it's been.
Okay, and that's what I kind of think, because there's been a couple of times that it's come up, and I feel like we need to know it to be able to talk about what we're talking about. So, okay.
Like when it equals 0, there's a min or a max.
Mm-hmm. Yeah. Yep, that's part of what we're talking about today. So, okay, so extrema on an interval. When I say extrema, I'm talking about maxes and mins, right? So get our vocabulary here. We're talking about extreme value theorem, global versus local extrema, and critical points. So max and min values of a function are called the extreme values. So if you're ever asked to find extreme values, extremas, you're asked to find maxes and mins. Usually extrema is what you'll hear me say. The process used to find to them is referred to as optimization. That's a lesson coming up here where we'll talk about what it means to optimize something. And there'll be times when we want to find the max and min for the entire domain or on just a particular interval. This lesson we're talking about how to use calculus to find extrema rather than a calculator. Because you can always graph a graph, right? And use your max and min features on your calculator to find that max and min. But that's not what we're talking about. We're talking about, okay, how do we use the calculator? What's the calculus behind it? Not just going straight to the calculator. So, so definition. Absolute global versus relative or local. So you guys have heard the word absolute. Excuse me. So I think you guys have probably heard the word absolute more. And then in terms of relative or local, I feel like I probably use relative more, but I think I've used local maybe as well. I just don't think I usually use the word global. You probably haven't heard global extrema. But absolute or global extrema is the absolute max. It is the highest point, or absolute min, the lowest point in the entire graph. So nothing else goes any higher or any lower than that absolute max or min. Here, for absolute global max and min, on an interval, if and only if f of c, so the value at the y value, is greater than the rest of the function for all x. So they're saying that there is, if at a certain point c, there's a y value that is bigger than all y values for any other x. Absolute. It is the highest value or the lowest value. Okay? And so, excuse me. Then, and I'm going to skip down here and talk about the definition real quick, but relative or local, any min or max can be relative or local because it's just a relative, it's a local, maybe in the neighborhood, okay? In that certain section of the graph, it is a min or a max, and that is relative or local. So y values on the graph of a function where the function changes from increasing to decreasing and vice versa, okay? Absolute or global, the highest or lowest y values on the graph of a specified domain of a function. Look at example 1 with me real quick. Determine the extrema of h of x on the interval a through f. So, give me a point and tell me what you see. What? E. Okay? So I'm assuming you're talking about right there, h of e. And what is that? Okay, so this right here is an absolute max. It's an absolute max because it is the highest this graph will ever go, yes? It goes no higher. So it is an absolute max. And that absolute max is what I will call f of e. And you want to, when you're asked for a maximum or minimum value, you're being asked for a y value. And f of e is a y value. Now, this max happens at x equals e, but the max value itself is f of e. Okay, so that's an absolute max. You could also technically call that a relative max. Okay, absolute maxes are also relative maxes, but more importantly, it's an absolute max. What else?
D.
D. What is D?
Absolute minimum.
Absolute minimum. The lowest the graph will ever go. Okay. So the absolute minimum is occurring at D, and specifically the y value associated with that is f of D. What else?
C.
So you have something happening at it? What would you call C? Or, well, at C, f of C, what would you call f of C? A relative max. Excuse me. F of C is a relative max, or you could say local max. And I'm going to say be interchangeable with those words, right? I hear both of those words quite often. One more point I want to talk about, and that is B. It's a hard point, but that doesn't matter. It is still a what? Relative minimum, or a local minimum of f of b. Okay? When we're talking about extrema, we generally are just talking about the pieces in the middle. We're not talking about the endpoints. Now, we will talk about endpoints here later, a little bit later on in this lesson, but when you're just asked to find extrema, it usually refers to the pieces within the interval. Okay. So, one thing I'm going to keep saying, extrema are y values. You can say they happen at x values. So like there's a relative min at b, but the relative min itself is f of b. Okay, so just keep that in your head. You have to watch when questions are asked. If it asks for the relative max or relative min or, you know, just extrema in general, we're looking for the y value. Okay. Definition of relative local extrema. If there's an open interval containing C, on which f of C is a maximum, then f of C is called a relative maximum. If there's an open interval containing C on which f of C is a minimum, then f of C is called a relative minimum. Again, it's just in the neighborhood, right? It's the min or max for that section of the graph. Some noteworthy thoughts is how it's listed here. When we say an open interval containing C, we mean that we can find some interval A to B, not including the endpoints, such that C is in that interval. So open interval means not including the endpoints, and that C is in between A and B somewhere. C will be, and that's the next point, C will be contained somewhere inside the interval and will not be either of the endpoints. A relative extrema is slightly different than an absolute extrema. Yes, they overlap, but an absolute extrema has a more specific definition, right? Whereas any min or max can be relative. All that's necessary for a point to be a relative max or min is for the point to be a max or minimum in some interval of x's around the point C. So that's an idea of being a min or a max in that neighborhood. Okay, so just in that little piece of the graph. and there can be smaller or larger values of the function at some other locations, but relative to point C, f of C is smaller or larger than all the other function values in the neighborhood of C. Okay? Now, in many cases, we'll be asked to analyze both open intervals and closed interval functions. So look at example 2 here. I think I'm going to make this a little bit bigger, so I'm not squeezing it in quite as much. Consider the graph of g of x shown at right. State the relative extrema of g of x. And then considering the domain for g, what are the absolute extrema of the function? Okay, what are your thoughts? Relative extrema? Give me one.
2, 2.
Okay. 2, 2. What is that? That is a relative max. And I'm not going to list as the ordered pair 2, 2. The relative max, I'm going to say, is 2 at x equals 2. And so by me saying relative max is 2, I'm saying that the y value is the relative max there. Okay, what else?
-3, -8.
Okay, what about -3, -8? What do we want to call that? Absolute minimum? Okay, now, how did, okay. Based on what I compared to the answer key, it's only listed here because it's absolute. Now, it's also relative for that section, right? So I honestly, I mean, I can understand if you put it both places, and I feel like that is done at times, because I think I did that somewhere else in my notes, maybe. Yeah, because then that's interesting. Because then I did that exact same thing down here on this graph. When I compared with the answer key, and yeah. So either way, I'm just going to list it here for right now. It's an absolute min. And what is the absolute minimum value? The absolute minimum value is -8, and it is occurring at x equals -3. Or if you say the absolute minimum at x equals -3 is -8, I don't care which way you say it. You just have to be careful there. And here. That could also be considered relative there. Or local. Okay, what else we have?
Local min.
What?
Local min.
Local min? 4, 0. So that is a relative or local min. And what is that minimum value? There's a minimum value of 0 at x equals 4. Okay. So we've got some relative extrema there. We've got an absolute min. Absolute max? We don't have one, do we? Okay. And that is because this graph is going infinitely up. Because those are arrows and not endpoints, we're not going to have an absolute max. So if we bring back a pre-calc word, this graph is what up top? If both pieces are going up, and away, remember talking about bounded versus unbounded? This is unbounded above. Okay, so I'm going to put here absolute max does not exist because, what is this graph? G g of x is unbounded above. That was pre-calc. We talked about boundedness, right? I don't know if we've reviewed it this year or not, but okay. Those other points are just labeled to throw you off, essentially, right? Not mins, not maxes, they're just points. Okay, consider the graph of f on 0 to 12. Find relative extrema, and then considering the domain for f, what are the absolute extrema of the function? So, relative, absolute. What are some points? Do a teensy bit more work. They're not labeled for you this time, are they? You have to count. Where are you starting at?
2, -2.
2, -2. And what would you like to call 2, -2? It is an
Absolute min.
absolute min. And I actually, in my notes, I have it listed in both places, but I'm going to go ahead and just put it here for right now. Absolute min. The absolute minimum value is -2 at x equals 2. Okay? And that is relative, so it could be listed up above as well. What else? Oh my gosh.
7, 7.
7, 7. And what is 7, 7?
Absolute max.
Okay, absolute max. It is the highest there, so absolute max is 7 at x equals 7. What's another one? And what is 10, 2?
Relative.
Relative min. So relative min is 2 at x equals 10. Did we get them all? Yeah. And both of these, I don't know, I'm realizing the notes weren't very consistent because both of these, when you look at the answer key, are also listed up here. But up above, it wasn't. So, again, anything that's absolute is also going to fall under the category of relative. Okay? If you're told to list extrema, I want them all. Okay? I want the absolute, I want the relatives. Okay? Or local, whichever way you prefer to say that. Okay.
Brody Miller, please report to the high school office. Brody Miller, please report to the high school office. Thank you.
I don't know who that one is. Okay. Next page, we're going to mention extreme value theorem. So what conditions would be necessary in order to have both an absolute maximum and an absolute minimum? So the extreme value theorem says if f is continuous, we keep talking about that, don't we? So in order for this theorem to apply, it has to be continuous on the closed interval a to b. Then f has both a maximum value and a minimum value on that interval. Okay, there is some max and some min on that interval. Extreme values can occur at interior points or end points of an interval. And so this is where we're going to talk about, besides just testing, and this will make more sense later, but besides just testing our interior points to find out their mins or maxes, we also have to include our endpoints. A function may have both maximum and minimum values over an interval, either a max or a minimum, or no extrema on an interval. And we're going to look at some of the examples here. Now, when the hypothesis or if statement is not met, either continuity or the closed interval, there is no guarantee of the conclusion then statement. However, a maximum, minimum, or both may still exist. There's just no guarantee. Okay, so a lot of these theorems we talk about in calculus are existence theorems, where it's just saying that, you know, something may exist, but it doesn't say that there's a guarantee. So you do have to be aware there. Okay, so example 4. As we look at A, for each graph, we're going to state whether the hypothesis of the extreme value theorem fails on the interval, and then we're going to determine if the function has an extrema on the interval. So whether or not the extreme value theorem applies does not definitely affect whether or not there are mins or maxes. Does that make sense? Okay, in other words, there can still be mins and maxes even if the extreme value theorem fails, because what is the what I want to say. What has to be true for us to be able to talk extreme value theorem? Has to be what? Continuous. What do you notice about graph A? It's not continuous, is it? Okay. So this is one where I'm going to say EVT, another abbreviation to add to your list. EVT does not apply since f of x is not continuous on the interval 0 to 3. EVT does not apply since f of x is not continuous on 0 to 3. And I say 0 to 3 because that is the interval where my graph exists. Now, when we talk about EVT, it's talking about basically absolute max and min. So, what do we have? What do we have in the way of absolute max and absolute min? Which one do you want to start with? There's an absolute what? Max at where? Yep. Absolute max is 4 at x equals 1. Where's the absolute min?
0.5.
Sounds like a good estimate to me. Absolute minimum is 1/2 or 0.5, and that is at x equals 0. And yes, we're guesstimating on a few of these, but we'll go with it. Okay. B. Does EVT apply? No, not continuous again, right? Okay, the theme this section. Okay, so EVT does not apply since not continuous on, what is it, 0 to 3 again? Okay. Thoughts on our absolute max and mins? What about an absolute max? Okay. It's an endpoint max this time, isn't it? Okay. So 4.5-ish, hard to tell with everything else, but absolute max is 4.5 at x equals 0. What about absolute min?
No, because it's
So this is what we want to call our absolute min, isn't it?
Could you say it's the limit of 1.5 as x approaches from the right? Could you say that?
We don't usually. I mean, because here's the deal, okay? And I see exactly where you're going. There is no absolute min as what we think of because this point does not exist, right? And it's not like we can say, okay, well, that's about 1, so I'm going to say 1.0001 is my absolute min. But exactly as Ethan said, it's a limit there, isn't it? It's not a specific number. It's that 1.0000, we can't even say that number because it's going right up to 1. We just don't know what it is. So for our purposes, I'm going to say no absolute minimum. Okay, now, totally get the whole idea of the limit thing. We just don't usually do that. Okay. So I'm just going to say there's no absolute minimum, at least not that we can specify.
So this theorem only cares about absolute.
Yes, yes. And I realized, because I was like, it doesn't really say that. But the idea is, if f is continuous, there is a max and a min. So that would be an absolute. And I guess it's more than anything, it's saying that there is one max and one min. It's just hard to say what the min here is. I mean, really, there is no other minimum here we could specify because that other point is right above it. And so that's really not a minimum there. Yeah, just a weird graph. Okay, C. Does EVT apply on the closed interval 0 to 3?
Yeah. Maybe.
Yeah, maybe. Okay, so the graph, for all basics' sake, appears continuous, yes? However, so we are specifically talking about the closed interval. Okay? If it was the open interval, I'd be all for it. But because it's a closed interval where the endpoints are included, what's the catch? This endpoint is not included, is it? Because it's an open point. And is the other endpoint included? This other endpoint is a vertical asymptote. So we could talk about it being continuous on 0 to 3, the open interval, but not on the closed interval. Because the idea of extreme value theorem is that we have to include the endpoints as well, and you can't include endpoints if they're not included. Is that making sense there? So, officially, we can say EVT is, or I just totally goofed up what I wanted to say there. Let's see. I'm going to say does not apply because not continuous again. And again, that's not continuous on the closed interval 0 to 3.
So like, have we even wrote what we're gonna write if it is applied?
Say that question again.
Are we gonna write something different when it does apply?
Well, on this one, we're basically just talking about, I mean, if you've noticed, for the most part, why the extreme value theorem here would not apply, looking at the continuity. But then still also realizing that there are often, not always, but there are often still mins and maxes. Now, if we bounce back to B for a moment, if extreme value theorem applied here, there would have to be an absolute minimum. But because EVT did not apply, there was, there didn't have to be a minimum, and there wasn't here. Okay?
So that can be.
Right. It doesn't, EVT, if it was continuous, it would guarantee that there would be. Now, C, do we have absolute max or min here? Absolute minimums, a fairly obvious no, because my graph is going infinitely down, isn't it? What about absolute max? Well, the place where we think the absolute max would be is an open hole. So, this specific graph has no extrema. Okay? And D. Does EVT apply or not apply? Doesn't apply because
The open interval on 0.
the open endpoints, right? The sharp point is okay. So realize the sharp point is not the reason we're saying it's not continuous. It's not differentiable, but the not continuous is because of the points at 1 and 3. So EVT does not apply on 0 to 3. Okay, and again, it's because of those endpoints there. Do we have some absolute maxes and mins this time? We actually do, don't we? Absolute max where? Or absolute max of? Absolute max is 4 at x equals 1. And what about absolute min? Yeah. Absolute min of -1 at x equals 2. Okay. Notice down there it says the extreme value theorem gives us a knowledge of when extrema occur, but how will we find them algebraically when given an equation only? So obviously when you're given a graph, it's much easier to find your mins and maxes. We need to talk about when you get some funky graph and you don't have a way to graph it, how do we identify where those extrema happen? So, example 5 here. For each function shown below, justify or explain why the extreme value theorem can be applied or why it does not apply on the given interval. Oh, that's right, we're not even finding them here yet. We're just talking about does it apply on this interval. So on the given function, 2x minus 3 over x minus 2. So that's some big function that goes on infinitely in both directions, most likely. We're specifically talking about on the interval -4 to 4. So this graph on this interval, -4 to 4. Would EVT apply and guarantee us an absolute min and max? Huh? Why not?
Because
I agree.
on the bottom, if you put like, 2, x equals 2.
You guys see it? What do we know about denominator? This function cannot exist when x equals 2. So what's that mean? It's not continuous there somehow or another. It's looking like a vertical asymptote, isn't it? Right? Because when your denominator equals 0, it's a vertical asymptote, unless there's a factor of x minus 2 on top that can cancel and be a whole. But a whole is not continuous either. So, for EVT to apply, we have to be continuous on this interval. Are we continuous from -4 to 4? No. And so, what do I have written? EVT does not apply on negative 4 to 4 because it is not continuous at x equals 2, which is contained on the interval. So EVT does not apply on the interval negative 4 less than or equal to x less than or equal to 4. And that can be written in the other way too. Because f of x is not continuous at x equals 2, which is in the given interval. Something along those lines, right? You're stating it's not continuous, and it's not continuous specifically where? At x equals 2. Like, that's your proof. You can't, I would not recommend just saying, oh, it's not continuous. Why is it not continuous? And if you're saying x equals 2, that's kind of the obvious of, oh, okay, they realize it's the denominator issue. Okay? Okay, B. E to the x minus 2 plus 1 on the interval negative 5 to 5. Now, the whole point is to do this without the calculator, right? E to the x minus 2 plus 1. Forget the plus 1. Forget the minus 2. Can you visualize an e to the x graph? Officially, I can go back to pre-calc and say it's one of your 12. I know. Been a moment.
Is it the stair step one?
No, definitely not the stair step.
It goes like we, and it starts.
Goes we. I'm not sure if you have the right angle of your we though.
You go.
Oh,
How about that we?
I was thinking of a different one.
Okay, I would say it didn't look like your drawing in the air did not look like it was going the right way.
Log one.
Okay,
Was it the square root? I think it's the square root.
log and square root would have the same shape. So, okay, so this is your exponential function. It could also be like if it was 2 to the x, 3 to the x, 4 to the x, 5 to the x. They'd all look like this, right? The minus 2 plus 1 just moves my graph right 2 and up 1. So right 2 up 1, is that going to affect my continuity here? No. So is this graph, does EVT apply here? Is it continuous on the interval negative 5 to 5? Yes. I didn't fall. It's all good. Okay, so I have written in my notes, g of x is continuous for all reals, so EVT applies on negative 5 to 5. So g of x is continuous for all reals, so EVT applies on the interval negative 5 less than or equal to x less than or equal to 5. I should have just put C on the same page, but I didn't. It's on my next page. So start thinking and looking at C. Speaking of that whole square root function thing. H of x equals x times square root of x plus 2 on the interval negative 6 to 6. Okay, I don't know. The whole x times square root of x plus 2 thing's a little weird, but think about that square root. What do you know about a square root?
It's funky when it's negative.
It's funky when it's negative. Because square roots essentially have to have positive values underneath the radical, right? So if you remember just the square root function is half of a sideways parabola, right? Now, I don't know, what does this times x thing do with it? Honestly, I don't even really know. But here's what I can look at, is that I know that x plus 2 has to be greater than or equal to 0. Any x value I put into this function has to make x plus 2 greater than or equal to 0, which means x has to be greater than or equal to negative 2. Can we talk about this function being continuous on the interval from negative 6 to 6? No, because any value I put into this function less than negative 2 isn't going to make it happen. Does that make sense there? Okay, so since h of x is only continuous on the interval x greater than or equal to negative 2, then EVT does not apply on the interval negative 6 less than or equal to x less than or equal to 6. Okay. We're getting ready to get to the back page, which is where we actually get to apply a lot of, finding the actual extrema. But, okay, so critical number. I don't know if I've ever defined critical number or critical value, or I don't know if the notes have ever defined, but it's popped up in our vocabulary a little bit. I know I occasionally will mention it. I know occasionally I'll see it listed in the answer key, that type of thing. But a critical number, or a critical value, or a critical point, all interchangeable, of a function f is an x value, x of c, in the domain of f, such that either the derivative equals 0 or the derivative does not exist. Okay? And critical values are where my mins and maxes are going to happen, which is, I'm jumping ahead of myself. So, if a number is a critical value, either the derivative equals 0 at that point, or the derivative did not exist at that point. Okay, those are your two options there, and we're going to talk about that. So, at that point, it is a critical point. Now, theorems leading into this, relative and local extrema can only occur at a critical value on an open interval. So, mins and maxes, right? They occur at critical value. Either derivative has to equal 0 or the derivative has to not exist for there to be a min or a max, basically. Absolute global extrema must occur at a critical point as well, or at an endpoint. So in other words, you have some big old function, but you're only looking at a specified interval, you have to not only consider testing our critical points, but we also have to consider the endpoints. Because if you have an endpoint that is higher or lower than the rest of that graph, that could be a max or a min on that interval. Okay, so these are the pieces that we're going to look at, is that these extrema occur at critical points, or an endpoint could happen as well. Okay, we're going to use something called the candidates test. I'm trying to think what else I've seen it called, but kind of going back to the idea that you did in pre-calc and maybe even algebra 2 some, where we're going to look at a number line a little bit and test things. Although I guess I'm not really using a number line in what we're doing today. So we're going to put these ideas together. We're going to talk about the candidates test to figure out where our absolute mins and maxes are. Yes, Megan?
When it says like the derivative will not exist, is that like there's a cusp or something?
Like a sharp point, or a sharp point, a cusp, also could be a denominator, because the derivative would not exist when the denominator equals 0. Yep. Okay. Find the absolute extrema of the function on the given interval, provided the EVT is applicable. If it is not, justify why. Now, it does say calculator here, but the calculator here is we're going to use it to get our y values when we need to. We're not graphing on it. I mean, that could be a check if you really want, but this is going to be used to find y values. Okay? Because we're looking at, okay, calculus-wise, how do we find our absolute extrema? So, in order to find these extrema, we need to start by finding the what? Derivative. Anytime you're asked to find mins and maxes, you're finding the derivative, setting it equal to 0 to find those critical points. So derivative. Did I do that math right? 24x squared minus 6x minus 9?
Yeah.
Okay. Set it equal to 0. If I set it equal to 0, I see a GCF I can factor out. GCF of 3. So I have 3 times 8x squared minus 2x minus 3. It does factor. This is where you guys are going to tell me product of AC, isn't it? And I will say, this is not the easiest one to be able to make it happen with just yes and check. Because 8x squared, it has options, doesn't it? 8x squared could be 8x and x or 2x and 4x. So we don't have, options there. Now, what do we know about 3? 3 is going to have to be 3 and 1, isn't it? I don't know. How talented are you with me today?
I think in the process of saving time.
Okay, well, and here's my deal. I need to get a negative 2x in the middle. So it's going to be 3 times whatever's right here and 1 times whatever's right here. And I need a difference of 2. So 3 times 2x will give me 6x. 1 times 4x will give me 4x. And a 6x and a 4x, if done rightly, can give me negative 2x, right? I'll need a negative 6x and a positive 4x. I don't know. Product of AC would get you there too. Okay, continue. Set each part equal to 0. Why am I even writing this out? What are my critical values? If I did my math there right, 3/4 and negative 1/2, right? These are my critical numbers. Okay. Now, critical numbers means there's likely some type of min or a max at each of those points. Could be something called an inflection point. Talk about that another day. However, we are on a specific interval here, aren't we? So we need to consider not only those 2 critical points we just came up with, but our endpoints as well. And so what is called the candidates test and what we're going to look at here is if I think x and f of x. Okay, well, I've got a negative 1 as an endpoint. I've got a critical point of negative 1/2, a critical point of 3/4, and a critical or an endpoint of 2. Are you guys catching where all 4 of those points came from? I need to know the y values for those. How do I find y values? Plug them into here, yes? Can I tell you today?
Yeah.
Negative 1 works out to be a 0. Negative 1/2 is 4.75. 3/4. 0.75 is negative 3.063. And 2 is 36. That is purely plug in your calculator and do the math, okay?
Wait, why did you do that?
Because I need to find my absolute extrema. Where is my absolute max? Where is my absolute min? So where's my absolute max? Which is the highest y value? 36. What's my absolute min? The negative 3.063. So my absolute max is 36. My absolute min is negative 3.063. And this is why, if we hadn't looked at the endpoints, we wouldn't realize that this endpoint is actually the highest point on that interval. Okay? Okay. I'm obviously at my stopping point today. However, I have, 4 examples left?
Well, I guess we can do the whole. It's only 3 pages, so it's not really well.
Yeah, the homework's not, I mean, it is 16 questions, and there's no parts A, B, C, D. It is 16 flat questions, if that, And what I'm trying to figure out, honestly, you've seen a little bit of everything. There's some catches, though. I'm trying to figure out how, because I want you guys to start looking at the homework, because I'm going to try and save part of a day here, I think, if that makes sense. So, I'm going to say, go ahead. I don't know, can you do all the homework or not?
Yeah.
We can do some of it.
Figure it out.
Huh?
Give her a shot.
That's the best I can ask for at this
It can
point.
save us a day, and we get another data.
Study for finals.
That's ultimately what it comes down to, guys, is the end of the semester here. So, okay, attempt the homework. Tomorrow, I may do a couple more of these examples. We'll start with homework questions. Second half, we may try and start doing it. So, we'll see what happens.